Welcome to this video on inductors. In this video we're going to take a look at what inductors do and how they behave in electrical circuits. And we will look at a little bit more of the theoretical nature behind the inductors, but we also want to take a look at just physically what's actually happening, because after all this is physics. So we're going to use a simulator here from the fet.colorado.edu website and have a link in the description below. This is the awesome circuit construction kit. It still uses the Java application to run, so if you have an iPad, unfortunately it won't work, but check it out because it's really helpful. So I'm just going to draw the circuit I have here, and then we're going to jump in, and instead of doing theoretical stuff first, we'll see what's actually happening. So I have a power supply or a battery at the bottom there, and then I have a resistor along the side. I have an inductor, and that's the whole star of the video here. The inductor is shown with this series of loops, and I have a switch. Right now the switch is open, and then I put an ammeter over here to read the current. Now I also have a voltmeter attached across this inductor because I want to see what's happening in regards to the current in this circuit and what's happening in regards to the voltage. So let's close this and keep a close eye on what's happening around here. Now there's some weird bug when you first start it, but it should go away. Okay, so I see the current is increasing, the voltage is dropping, and I see that the current is starting to drop. It's starting to increase, but the rate of change is decreasing. So it's increasing at a decreasing rate, substantially decreased now, as it looks like it's approaching 0.9 amps, and the voltage looks to be decreasing towards 0 across the inductor. Alright, so at this point the voltage is still dropping, but the current is pretty much stopped. So based on this physical observation here, let's just create some graphs of this so we can think about what's happening. So if I make a current versus time graph here, let me go ahead and pause this. We have a current versus time graph. What we saw happen was that the current pretty rapidly increased, but then it started to decrease the rate at which it was increasing. And it reached basically a steady state, which is reaching essentially an asymptote. So it exhibits some asymptotic behavior, and we could think about what that value is here in a minute. The voltage as a function of time across, specifically across the inductor, and we symbolize inductor with the letter L, uppercase L. What we saw happen here was that we started with some fixed value, and it monotonically decreased towards 0 volts. So there was some sort of asymptote here along that 0 line. Now for those of you who've been watching a lot of the videos in this AP Physics C or calculus-based physics videos, you notice that these graphs look very much like the graphs for drag and the graphs for the charging and the discharging of a capacitor. And that is because they are also exponential relationships. So this one was a logarithmic or exponential drop here, and then we have this increase that's kind of leveling out. So let's think about physically what that would mean if something like this is happening. Well, if we think of it in terms of drag, we know that the object is falling and its acceleration is dropping towards 0. For the velocity, we know it's reaching a terminal velocity. So basically what's happening is that there's either becoming less and less resistance relative to the movement, right, or there's just becoming less and less pushback, if you will. So in this example over here, if we were to get rid of the inductor and just take a look at the graph of current versus time, it would be a little bit boring because it would just be what this asymptote is. And you could calculate it using if you had just this one resistor, you could use Ohm's law, okay, and you'd see that the current was equal to EMF divided by the resistance, and that would be the asymptote value over here. So essentially what's happening is we don't have the maximum current we should have, and that would imply that there's either more resistance or something's taking away the potential across the circuit, and it's pushing against that, and eventually it pushes, and it's almost as that it's winning out, right? There's less and less resistance. So you could almost think of the difference between the asymptote and any point on this function as being the amount of difference that we're lacking, that we're experiencing for each given amount of time, but the difference is decreasing as time passes up to that point. And the voltage, we're seeing the almost the opposite happen, but really what we're seeing is this thing not having as much of a voltage drop. Now, what does that actually mean, to have a voltage drop? Well, if you think of the amount of work being done on charges that are moving through the circuit, that what you're essentially saying is that initially the amount of voltage potential difference on either side of the inductor was some maximum value. So we were experiencing some work here. The inductor was doing negative work on these charges because we can see that the charges are being stalled from what the battery is pushing them to achieve, right? But as time went by and this potential difference dropped, the amount of work that the inductor was doing against the electrons decreased. And so the energy here, there's some sort of an energy play, right? We're seeing that we're either using up a lot of energy to fight against this inductor, that's one way to look at it, or the inductor is demanding a lot of energy and using a lot of energy from the circuit. So physically speaking here, what we're experiencing is some sort of pushback. And that's what we're going to put here, is a pushback from the inductor. And that's essentially what the inductor is doing in the circuit. But it depends how the circuit is running. And we're going to see that as we go along. Now, two of the most important things that we're going to look at, and we'll probably look at it in the next video, just to get a little bit more time, is that if you think about Lenz's law and you think about Faraday's law, we know that it has something to do with the fact that change is always opposed. And it's not by choice, but it's by the natural response to a change. Anytime something is pushed, it's going to push back because it can't create energy. It's just responding to what's happened in the past. So we know that the EMF, or this, what we could essentially say is this voltage across the inductor, is going to be equal to negative, this is the Lenz's law part, right? It's going to always be oppositional, times the number of turns times the rate of change of the magnetic flux. So what we see is that the change in flux that's happening here in this solenoid, the more change that we experience, the EMF response is in a certain kind of position. But we see that that change is dropping over time, or the change is reducing over time because there isn't as much pushback. And so what we're going to do is we're going to use Faraday's law and indirectly Lenz's law to set up a differential equation in order to solve for how the current varies with time. So in the next video, we're going to take a look at how we can actually get this function now that we've set up this idea, and we'll take a little bit of a closer look at what the inductors are doing.